Hi, everybody. Welcome to the September San Jose Astronomical Association imaging meeting. And tonight we have Julien Lecomte, and he's going to show us all the cool things you can make with 3D printers and such for amateur astronomy. So take it away, Julien.
All right, can you hear me?
Yes.
Perfect. All right. So thank you everyone for having me. By the way, I used to be an SJAA member a long time ago, over 20 years ago in the early 2000s. And I used to attend your general, I think it was called the general meeting every month, where they had usually a scientist presenting. I don't know if you guys still do that, but I really enjoyed doing those. So yes, thank you for having me. And in tonight's presentation, it's going to be a little bit ambitious. So it's about engineering custom astronomical accessories using technologies popularized by the maker movement. It rolls off the tongue. So in this talk, my goal really is to inspire you to maybe take the plunge with some of these technologies. Or if you've already taken the plunge, maybe it will give you new ideas. And stimulation is always a good thing with this kind of thing. So let's get started. There you go. All right, a little bit about me, first of all. So my name is Julien. I was born and I grew up in France, in the French Alps, just across the border from Francesco, and about 40 kilometers south of Geneva. And about 20 years ago, a little over 20 years ago, I moved to California right after I graduated from university in France. And this is where I've worked since. So I'm a software engineer by trade, which is not surprising here in Silicon Valley. And that GIF is an accurate depiction of how I spend most of my days. I love to make stuff, and these are some of the pieces, the woodworking pieces that I've made over the years. So two of these actually were featured in Fine Woodworking magazine, if you're familiar with the magazine that you can see on the stands. So yeah, I love making things out of wood. I make those in my garage, and I haven't done much woodworking lately, but this is something that I would like to do more of when I'm retired. I still own the wine cabinet, the dresser, and the fiddle card table here. I even designed my own telescope, a 16-inch f4 telescope with a lot of guidance from Albert High. Maybe some of you know the name, a fantastic guy who actually wrote a book that was published with Wilman Bell, I believe. And really a great engineer and somebody who was very generous with his time to help me. So you can see here a depiction of the telescope before I built it. This was done in 2010, and that was that 3D modeling was done with AutoCAD, and you can see some of the steps of the fabrication here and the finished piece. And I still use it today. It's an amazing piece of engineering. A very simple telescope, but it works very, very well. So my interest in astronomy dates back to about 1990. So we're talking like over 30 years ago. I was 11 years old. And I remember I was bored on a summer afternoon, and I went to my dad's office and was looking at the books in his bookcase, and one of them caught my attention, and that was a 1950 edition of this book, Astronomie populaire by Camille Flammarion. And so I basically took it from my dad's bookcase with his permission, took it to my room and started reading it. And I just became really fascinated with astronomy. And I've been ever since. So through the years, mostly I've been a visual observer. And I was very active back in 2008 to 2012. During that time, I completed the Herschel 400 Astronomical League project, and I did about 70% of the Herschel 2, kind of lost steam towards the end. but I've always loved doing visual observing. And so I became interested in astrophotography only a couple of years ago. So what happened is you probably all remember Comet Neowise. And I remember getting up really early one morning, and I drove to Santa Teresa County Park with a little DSLR camera and a tripod. And I was trying to take a photo of the comet. And I mean, it came out horrible, but I was blown away by what was possible. So I was like, this astrophotography thing looks kind of fun. So I decided I was going to give it a try. At the time, I didn't want to invest too much money. And the reason is that at the time, I was under the impression that you had to have the darkest possible skies in order to do good work. And so I kind of knew myself, and I was like, if I'm going to invest a bunch of money and then I only take it out like once every couple of months, it's not going to be a good investment. But then on YouTube, I stumbled upon a YouTube channel called Cuve the Lazy Geek, who happens to be also a Frenchman, although he lives in Tokyo. And he really inspired me by showing that it was actually possible to do imaging from urban areas and not just narrowband imaging, actually get good results in broadband imaging. Of course, not as good as what you would be able to get in a dark sky, but enough for me to realize that my investment was actually worth it. I was also inspired by another Frenchman called Christian Buil, and I'll talk more about him later. He was a pioneer of the adoption of CCD cameras in the 80s and 90s, primarily in France, and he's also an expert in spectroscopy. So through the years, my equipment has changed a lot. So back in 1990, I started with a 60mm refractor. Then I upgraded to a small Newtonian telescope that was on a wobbly equatorial mount. 1997, I was able to save up enough money to buy a Meade 8-inch LX50, with which I was able to do a little bit of planetary imaging using a webcam, and I had built a little adapter for it. I got decent results. Then 2002, after I moved to the US, I bought a Meade ETX 105 and I loved it. I loved the go-to functionality of that telescope. It actually worked really, really well. And I was also taking photos of the planets from my condo in Milpitas. Then in 2008, my wife gifted me a Meade Lightbridge 12-inch Dobsonian telescope for my 30th birthday. And I just loved it. That's when I really got back into astronomy and really enjoyed observing under dark skies. 2010, I made that 16-inch Dobsonian telescope I showed you earlier. And then just recently, a couple of years ago, I purchased a 130mm, so a 5-inch triplet refractor on an Ioptron CEM70 mount. So that's what I currently use for astrophotography. All right, so what does it mean to be a maker? So first of all, I'm not a huge fan of the term maker. I mean, nothing wrong with it, but maker, tinker, I don't know. I like the term engineer, and you don't have to be an engineer by trade. You can just have an engineering mindset, a curious mind. And so I think that represents me, and it also, I'm sure, represents a lot of you, because amateur astronomy, especially astrophotography, is a technical hobby, and you have to have a bit of an engineering mindset in order to troubleshoot the issues that we all encounter during a night of astrophotography. So why make things in amateur astronomy? Well, in my case, there were several factors. The first one was the price of some of the equipment that I needed. For example, I needed an ASCOM compatible flat panel, and the ones that you could find on the market really were outrageously expensive. So I kind of decided to make my own, and this is the unit that I came up with. And this unit—
Do you want to unshare when you show those things?
Oh, okay, that's fine. I'll show them at the end.
Okay.
Yeah. So anyway, the price of that unit on the market was really, really high. And so I decided to build my own. And it turned out to be actually better than what I could find and cheaper. And in some cases, there are things that you just cannot find on the market at all. Either the availability is very low, or it's no longer available, or it's not exactly what you need. Maybe it's too big, maybe it's too small. There's always little things. So being able to make some of the things that you need is really powerful. Also, with the pandemic in the last couple of years, I'm sure you all know that sometimes it's difficult to get equipment. Sometimes there are long lead times. So anyway, these are some of the reasons why I decided to make accessories myself, design them and make them. So let's talk a little bit about the tools of the trade. And the first step, we'll talk about 3D modeling software. And I'm only going to name a small number. I'm sure you guys might use others. I didn't want to talk about SketchUp or other, but these I think are the most popular ones. So Fusion 360 by Autodesk is probably the most popular 3D modeling software. I don't use it because I'm not a fan of their licensing model, to be honest. And I'm seeing a tendency that Autodesk has to slowly but surely pull features away from their users. They started about a year ago and it'll probably continue. I wish they offered a license at a lower price for hobbyists and without any restrictions. So, but anyway, Fusion 360, I think, is the gold standard, and it's a really, really good software. Tinkercad, I believe, is also by Autodesk. That's a completely web-based application, and it works really well for simple models. So something to keep in mind, and it's free. I decided to use FreeCAD because, to me, learning how to use a 3D modeling software is a very time-intensive activity. It takes a lot of time to master that kind of software, and so I wanted to invest my time into something that would not disappear from underneath me. And FreeCAD is free software, it's open source, and there's a strong community behind it, so it will live on. And it's been around for 20 years. It's not the greatest. There's a lot of bugs, and there's things that I don't like about it, but for the most part, it actually works really well. OpenSCAD is another one that's free and open source. And some people really, really like it. I decided to use FreeCAD, but OpenSCAD is also another good option. 3D printers. Let me talk briefly about my 3D printer, but before we get into that, let me explain why I got into 3D printing. So I actually got into 3D printing earlier this year. So I'm by no means, I'm not an expert at all. I actually consider myself a beginner. And I remember about a year ago at CASTAR, I had a conversation with Mark Johnston in the afternoon, and he was showing us some of the pieces that he had printed, and he was very proud of it. And I kept making fun of him, saying, 3D printing, it's a solution in search of a problem. And, we were all laughing. But then I came home and did a little bit of research, and then I realized it's actually pretty good. so I ended up investing into a budget printer. So this is a Creality Ender 3 V2. Which costs, I think I paid $250 for it on Amazon, and it comes as a kit, and you just assemble it. There are a lot of YouTube videos that show you how to assemble it correctly, which is very important. And then it actually works out of the box really well. I mean, my first print was amazing, and so I printed one of those calibration cubes, and it just came out perfect. So I thought, wow, this is amazing. But I ended up having to do a few upgrades for things that I needed. So for example, stiffer bed springs, that's really important. And those are really cheap so that your bed doesn't go out of alignment. The BL Touch, can you see my pointer? Yeah. Okay.
Yes.
The BL Touch is that little probe here that sits on the side next to the extruder, or next to the nozzle. And that is really important because by default, this unit uses micro switches for all three axes. In X and Y, it's not a big deal, but the accuracy of the end stop on the Z axis has to be really high. And these micro switches just are not accurate enough. A BL Touch probe will get you the precision that you need, which is below 0.1 millimeter. So that was a really amazing upgrade. And then I got an all metal hot end. So I got the micro Swiss unit, which allows me to print up to 260 degrees. So I could print PETG. PEI sheet is that little thing here, and that makes it really easy to get the parts off of the printer, especially large parts. And then a free upgrade was to also update the firmware on this thing. And the Gyros firmware is a really nice piece of software. So I really recommend it. But overall, I think I paid about $350, which, you know, it's not super high. And it's a really, really well, it works amazingly well for the price, I think. A lot of other small parts and things that are needed. So metric taps. So usually you try to avoid making threads in plastic because they don't hold very well. But in some cases it can be helpful. So I have a set of these. It's really cheap. And then, you know, a bunch of nuts and bolts and threaded inserts. That's also a really important thing in 3D printing. These are inserted into holes, and I use a soldering iron to heat the threaded insert, press it against the part, and it basically like fuse with the part that, and then it makes a threaded insert that is that will not go bad over time. Let's talk about electronics. So because obviously this is not all about 3D printing, electronics is an important aspect of what I do. And so you'll need to invest into a small number of tools in order to get started. So I actually bought an Arduino starter kit, again, off of Amazon for, I think, $19. It was really cheap. And I recommend it to adults. I recommend it as a gift to teenagers. If you have a teenager and you don't know what to give them for Christmas, an Arduino starter kit is an amazing gift, especially if your kid is technically inclined. So that's one thing. And then, you know, some equipment for soldering, including a soldering pump. Really important. Sometimes it'll save your bacon. A multimeter with an oscilloscope, whether it's a separate unit or included in the multimeter, especially when you have to debug PWM signal. That's really important to have an oscilloscope. PCBs, I like these, which also you can buy pretty much everywhere, and then you just solder your components. If you're really advanced, I guess you could design, if you're creating really complex circuits, you could design them in software and then have the PCBs printed professionally by companies like PCBWay. And I've never gone through that route. Usually the circuits that I create are relatively simple, and I only need to make one. But if you need to make a bunch and they're a little complex, maybe create it in software and then have a company make them for you. Electrical wires and stripper. Name a man who doesn't like to have a stripper in his house, right? So this is a really important tool. And then of course, miscellaneous components and connectors. And let's talk about the software. So Windows is really important in astrophotography, unfortunately, but you know, it is what it is. Like the ASCOM platform is, the ASCOM Classic, I should say, is only for Windows. So all of the drivers for all of the devices, they're all on Windows. So it is an unfortunate reality, but you know, it's not that bad either. Microsoft Visual Studio is actually surprisingly good, I'm afraid to say. I remember when I started my career here in the Silicon Valley, I used to use Microsoft Visual C++. It was pretty terrible at the time, although it was already the best, but it was pretty terrible. And just recently, when I started using Microsoft Visual Studio again on Windows 11, so Visual Studio 2022, I was actually surprised. It's really good. And so they made a lot of progress. Arduino platform, Arduino IDE, that's a really important thing if you're doing any kind of embedded circuits. And then I mentioned Python and AstroPy because those are more and more common, and a lot of people write software for astronomy using Python and AstroPy. Okay, let me cover a core principle of the maker movement. And so I hope that if you guys build your own devices and think that you came up with something unique, sharing is a really important aspect of what we do, which is what I do. So share your work with others. The first thing I want to mention is people often don't share enough. I remember when I was working on my automated telescope cover, I did some research on YouTube and other sources, and I was able to find people sharing their devices, but almost no explanation. They weren't really sharing any of their code or 3D files, and people in the common threads kept asking, hey, can you share your electronic circuit schematics, and can you share your code, put it on GitHub, whatever. And a lot of people, they either don't, or maybe they created something unique and they just keep it for themselves, which is kind of a shame. So sharing, even if you don't think that your work is amazing, I think it still has value. Publish your code on social coding platforms. So I use GitHub, and all of my code, all of the things that I do is published on GitHub, and it's available to anyone who wants to see it with a lot of explanations. There are a lot of other coding platforms like Bitbucket, but basically use something that allows people to ask questions and also submit contributions so that together we can make better software. Don't hesitate to share your work, even if you think that it's not complete, if you think it's just a proof of concept, even if you think that your code is embarrassing, and sometimes I think my code is embarrassing, or maybe sometimes it doesn't work. Maybe there's things that still, maybe there's a few corner cases. It still has value to share that code. And some people might find it stimulating, might come up with new ideas, might contribute some of their time to make your software better. Document your work. It's one thing to put your code up on GitHub, but it's much more important to actually document it, ideally in the same code repository, for example, in a README file, so that it's easy for people looking at the code to go through the instructions, to know how to compile, how to install the software, how to use it. Make sure that you use a permissive license. So all of my software is published under the MIT license, which allows people to use it in, someone is snoring. Did I put someone to sleep? Can you mute Ming, please? Thank you. All right, so I use the MIT license because it is a permissive license that's.
I just muted everybody, Julien, including you, so you have to unmute.
Thank you. All right. So yes, the MIT license is one of those licenses that allow you to publish your code. It can be used in commercial products, and that's perfectly fine by me. You may want to avoid GPL licenses because of, but I'm not a legal expert, but I know enough about GPL that a lot of people want to stay away from it. And finally, avoid patents. So here's why I'm putting this in this slide. I recently watched a video of a guy who came up with something that was really neat. It had to do with the Celestron rasa. And he made a system that allows him to easily take flats with his Celestron rasa. So I thought that was, oh, that's kind of cool. And in the comment thread of his video, he's mentioning that he's thinking about filing a patent. My reaction was to roll my eyes and said, you know what, we're not really in this hobby for, you're not going to become a millionaire of a device to take flats with a Celestron rasa. Let's be real. So to me, there's a lot more value in just giving your work for free and just let others enjoy it and maybe even they will help you make it better. So, please don't avoid patents. All right, and then, it's one thing to do your work and publish it, but it's important to evangelize it as well. So, start a YouTube channel or a website or a blog. Post about your work on social media or in amateur astronomy forums. So I like Cloudy Nights. In France, there's a very famous forum called AstroSurf, but there's many others. A tech talk with your local astronomy club, like SJAA, I think is a great venue to share some of your ideas and share some of your experiences with like-minded folks. Star parties are a great place to see equipment in action and get new ideas. I remember, one thing that I love to do when I go to star parties like CalStar or GSSP is whenever I go out and meet up with friends at a dark site, I like to look at their equipment and see what they did. And I remember last year at GSSP, there were quite a few people from the Santa Cruz Astronomy Club, and they had really neat devices. One guy had a mount that he had made out of wood for his binoculars. And I thought that was a really neat piece of engineering, something that, I took some photos and I wanted to eventually replicate it. So yeah, star parties are a great way to see equipment in action, maybe even try it out. Present at conferences or star parties. And then one thing that's important, and that's always something that I do, is focus on the process, not the product. A lot of people will ask you for your STL files and the code that's ready to go, as in you'll be providing them with a product. No. My point of view is you give them the tools so that they can build the device on their own, maybe give it their own twist, maybe simplify it, make it more complicated, but you don't give them a product, you give them a process that they can follow, understand, and then build the product on their own. That's a lesson that I learned from one of my woodworking instructor, who was really great at teaching woodworking by focusing on the process, not the product. All right, so now let's get into the meat of this presentation, which is I'm going to talk about some of my recent projects. So starting now, if you have a question, you can interrupt me and we'll take a break and I'll answer your question and then we will continue, okay? So like I mentioned earlier, some of the projects that I've done are not hardware projects. They can be just pure software projects. And so this is something that I did a while back, which allows me to, so there's always the question of, okay, I want to upgrade and get a new telescope. What combination of aperture and focal length and pixel size and seeing, how can I optimize my investment in order to get the best resolution in deep sky imaging? Okay, so that was kind of the question that I was trying to answer. And that was in response to a video that I saw on YouTube where I think that the author had made a few mistakes in his presentation. So I wanted to have something that was more formal. And I created a piece of software using something called GNU Octave, which is, you might be maybe familiar with MATLAB, so mathematical simulation software. GNU Octave is a free version of MATLAB, free as in free software. And it's actually really good. It can do probably, I don't know, 70% of what MATLAB can do. and it's actually compatible with MATLAB in many ways. So I created this thing, and this was the output for different set of input parameters. So on the left, you can see graphs for a 4-inch refractor f7 with a ZW ASI 1600. And then on the right, in Celestron 925 at f7, so with a reducer with a ZW ASI 294. And then you have a single star and then double stars, a double star that is separated by 2.5 arcsecond. And then I also have a seeing that is set to what's average in my location. So if I measure the FWHM of stars in my exposure, when I take them from my backyard, I usually get about between 2 and 2.5 arcsecond. So that's representative of my seeing conditions. But that's also one of the input parameters in the software. And so this is actually what you get. And you can see that, you know, unsurprisingly, the larger telescope with the smaller pixels give you higher resolution than the smaller telescope with the bigger pixels. So again, not surprising, but this software allows you to play with a few parameters and try different things. And I thought that was really interesting. One thing that this taught me is that seeing is really the limiting factor when it comes to deep sky imaging. I mean, I'm sure all of you guys know that because this is the imaging special interest group, but that's something that I didn't know. Again, I started astrophotography only 2 years ago. And I realized that, you know, unless I move to an area where seeing is a lot better, it probably would not be very useful to have a very long focal length unless I use a sensor with very large pixels, which is actually a really good thing. Unfortunately, most sensors nowadays have relatively small pixels because most of the sensors are made for the consumer market. Okay. So I invite you to check out this GitHub repo here. The link is at the bottom. And then there's a lot of explanations in the README file and to show you how to use it. All right, so this was my first hardware project for my telescope. And that's a Losmandy dovetail clamp. So let me explain. I have two pieces of equipment that ride on top of my telescope. The first one is a mini PC. That's the Melee Quieter 2. So it's a fanless PC. And then the second piece of equipment is a Pegasus Astro Pocket Power Box Advance, right? To use as a USB hub and power distribution, and also as a dew heater controller. So I wanted to have a nice, clean way to attach those to the back of my telescope because in the beginning I was just using Velcro, which, you know, Velcro is kind of, it works for a while, but it's not ideal. So I came up with something that I thought was kind of cool. So I have a Losmandy dovetail on the top of my telescope here in black. And I made these little things here and they have all the holes necessary to attach the computer and the Pocket Power Box Advance. Right, so you can see what it looks like. I even made these knobs on my 3D printer. And these knobs are actually made by, I went to Home Depot and I purchased a long bolt with an X head. And then I basically made designed in 3D modeling software, designed the head here and pressed the bolt against it. So yeah, this is kind of how I made it. Relatively simple, but you have like two parts to it. And there's a little spring here also. While I was printing the body of the clamp, you see there's a little hole here, and you basically drop a square nut into this hole. You can actually, technically you can pause the printing, but when you pause the printing, sometimes you get artifacts on the side of the piece. So what I did is I waited until the print head was off into the corner, and then I basically just dropped that square nut into that hole, and then it just prints on top of it. So it becomes kind of imprisoned inside the part. Yeah, so that was kind of a fun project to design and to print, and I was encouraged after I made this. Gave me a nice clean solution to attach my equipment. Okay. Any questions so far? If you guys have any question, make sure that you unmute. All right, no question. Great. All right, so the next project is a lot of fun. So I ran into an issue one day. So usually what I do when I image from my backyard is I set up and then I take the cover off, start my sequence, and then I usually go to bed because, well, like most of you guys, I have to work the next day, and the telescope does its thing. And 90% of the time it works pretty well. But there was that one night when the fog rolled in, and which was completely unexpected. And the fog was actually really bad. And I got up in the morning. Well, first of all of my images after midnight were completely white. Not a big deal. But my objective lens was really nasty. And there was like almost water at the bottom and then dots everywhere. Oh my God. So I had to very carefully clean it. And I'm always very careful when it comes to cleaning optics. It's something that I want to do the least amount possible. So then I figured, well, it would be good if I could automatically open the telescope when the sequence starts. And sometimes my sequences start like 1 a.m. And then automatically have the cover close itself when the sequence ends, which can be when there are clouds that are detected. So I wanted to make this ASCOM telescope cover. And it took me a little while to figure out how to make it. I saw a few on YouTube, and unfortunately people weren't sharing anything, which was kind of it was a little sad. So it took me quite a while to reverse engineer how to build that. But in the end, it was actually not that difficult. So you can see on the left here, there is the 3D rendering in FreeCAD of the finished product. And then you can see it here working on my telescope. That's when I was adjusting it. This here is a, what do you call that? I forgot the name. It's like, it's a ring clamp, I think. There is felt on the inside, so it's not going to mar the the paint on the telescope. Yeah, it looks a little ghetto, but it works pretty well. So let me show you, I think, okay, so let's talk about the electronics. Very simple. So there's a microcontroller with, microcontroller with a USB-C port. I got the Arduino Xiao because it's a very, very affordable microcontroller, $5 a piece. So, I bought 10 of them. They come from China. It takes a couple of months to get them. And they're really small. They're the size of my thumb. And I got a servo, which is able to turn 270 degrees. And then because I use a 12-volt power source for everything, I needed to reduce that to 6 volts, I believe, for the servo. So I used a buck converter. So in this case, it's called a Mini 360, which is an adjustable buck converter. And again, super tiny component. And you can see the finished circuit on the right. So again, the microcontroller is here. You can connect your USB-C cable here. There's the buck converter. And these are the wires for the servo. So ground, VCC, and the signal to control it. And here's the 12-volt DC input. very simple circuit, okay? And this is, hopefully you'll be able to see the video. So there it is, working in my garage. And like I said, it works amazingly well. So this is something that I use all the time now. All right. All right, so any question regarding this?
Can I ask a question?
Please.
So first of all, so the microcontroller, I assume that's a little computer where you download a program via USB. Is that what that is?
Actually, it's not. A microcontroller is not at all like a computer. So a microcontroller, the main difference, to simplify things, the main difference between a microcontroller and a computer is that a microcontroller, when you power it up, immediately it's available, right? Whereas a computer, there's an operating system, it takes a little while to boot up. So if you look at the Raspberry Pi, for example, and also a Raspberry Pi is a microcomputer, right? It's also a lot more expensive. A Raspberry Pi is quite a bit more expensive. I don't know how much they cost nowadays, but a microcontroller it's just basically a small chip that you can program. And we use the Arduino software platform. You know, when you hear the word Arduino, it doesn't refer to a hardware platform. It doesn't refer to a microcontroller. It's actually a software platform that allows you to, that basically gives you sane APIs to program your microcontroller.
So
but basically,
the bottom line, you program it in advance.
Yes.
And then when it powers on, it's a real-time operating system that just executes some program.
Yeah, I wouldn't call it an operating system, although it's possible to run an operating system on, or even like a super simple operating system on a microcontroller. But basically what I do is, ahead of time, I flash the firmware. So I develop the firmware in using the Arduino IDE, and that's done in C++. And then you compile it, you connect it to the USB-C connector here, to your computer, and you upload the firmware to the microcontroller. So it's stored in the memory, the flash memory. And then when you power it up, it's going to start executing the instruction that you gave it, right? So maybe I can show a small sample of what the firmware looks like. Let me stop sharing. I'm going to try to share my entire screen. And let's see if this works. All right, can you see my entire screen? Yeah. Okay, perfect. So let's look at the firmware for this guy here. So by the way, this is all of the GitHub repositories that I share. And you can see here the ASCOM telescope cover, and it's got a lot of documentation. So I invite you to check it out. But if you look at the Arduino firmware, this one is very simple. There are two functions. The first one is setup, which is run once when you power up the microcontroller. And the other one is loop, and that will execute in a loop forever until you power it off, okay? And so when you in setup, of course, you have to set up a number of things. So like, for example, initializing the serial interface, initializing the servo, and then do a few things related to LEDs. And then in loop, I wait for commands coming from the computer. And then when I receive a command, I basically handle it. So for example, if I get the command open from the computer, I invoke open cover, and open cover basically reads the position from the servo, and then incrementally in the loop, I change the position of the servo and then wait, change the position of the servo and wait, and so on, right? All
right, that's pretty clear. And so one last question then, from one software engineer to another. So what happens when you follow a null pointer or something like that? Does it crash? Does it restart the loop?
That's a good question. So I've never actually been faced with that.
Oh, that's impossible.
I mean, yeah. I mean, the thing is, if you use an operating system, like a modern operating system, when you try to write to a part of the memory that you don't have access to, there is a protection that is set up at the CPU level by the OS. Remember here, there is no such API at the processing unit level, and there's no operating system. So you can literally do whatever you want. And what happens if you do something crazy? I don't know, actually. That's a good question.
So in other words, if you overwrote, I guess you can't overwrite the program. It must be in read-only memory or something.
Yes, yes.
But you could conceivably jump to a location where you're executing trash, and then it will, not like if you corrupted a stack, and then you would think it would go away forever. So another approach to this would be, like some kind of execute to completion, and then, restart every, millisecond or 10 milliseconds, but whatever. Yeah. Thank you.
Sure. All right.
Okay. I have another question here. How did you integrate this with your imaging software? Like, are you manually sending commands? How do you start, stop?
Oh, that's a good question as well. Great. See, this is why I like these questions. So to integrate with imaging software, you don't really have the choice. You have to use ASCOM. So I created an ASCOM driver for it. And the ASCOM driver is very simple. In this case, it is, I use the iSwitch V2 interface. So it is seen by the imaging software. In my case, I use Nina, but you could technically use anything you want. It is seen as a switch. And so as part of my sequence, one of the very first instruction is to turn the switch on, which basically opens the cover, okay? And so in this driver, what I do is, all this driver does really is connect to the device, to the microcontroller, and then send it commands. So for example, if we look at, let's see, if we look at that switch here, if you pass through, it will call open cover, and open cover basically, let's see, what it does is it sends a command followed by separator to the serial interface. Okay, and close
so
cover.
everything is serial, and the microcontroller has a USB to serial.
Correct. Yes.
Adapter or something built into it.
Correct. Yes. Yeah, you don't want to deal with USB.
Right. Exactly. Yeah. Serial is a lot simpler.
But
right.
I wanted to chime in here that one of the things that you can do with the Arduino is, if you can, if somebody has reverse engineered the serial protocol that something uses, right, then you can reuse their driver, right, and you just have to have the Arduino respond to the serial command. So like, we've done focusers and rotators and other things. The flat panel, right, using pre-existing drivers for a commercial product or other.
Sure, but I mean, usually the creation of the driver is one of the easiest part of the process. At least that's been my experience. And towards the end of this presentation, I'll show you how easy it is actually. Okay, any other question before I move on?
So from the from Nina, is there like a switch device that you can add to Nina or something?
So in Nina, if you go to the equipment tab, and then you go to the switch or switches tab within the equipment tab.
Oh, okay. So there is something that you can hook this up to.
Yeah, as long as your...
And it's just a COM port that it'll show up as.
Right, as long as your ASCOM driver has been registered, it will show up in the dropdown. Yeah. I'll show you what it looks like later with another type of device. It'll
Perfect. Thanks.
Okay, let me move on. And okay, so circular LED strip flat panel uniformity simulation. So this is kind of fun. So I mentioned earlier that I wanted to build an ASCOM compatible flat panel. I had some constraints. I wanted something that was not too difficult to build, relatively affordable, that had good uniformity, and that, of course, I could control using the ASCOM protocol. And also, I wanted something that was not too big, that was just the right size for my telescope, right? I mean, because some people have come up with solutions that involve, okay, you buy one of those LED tracing panels off of Amazon, and you open it up, you remove the electronics, and then you end up with a giant panel that is like 2 times the size of your telescope. Okay, I wanted something that was just the right size. And also because it takes a lot less room to pack. Okay, so the question is, how am I going to do this? So my first idea was, okay, so if I put imagine a round, flat, white surface, and then just above it, along the perimeter, you put an LED strip. You know, I'm sure you've seen LED strips. You can buy them on Amazon for a couple of dollars. They're used for decoration. So I thought, okay, so if I have a white panel, round white panel, and then on top, along the perimeter, an LED strip, okay, facing inward. And you put the LED strip a few millimeters above the flat surface. How uniform is that flat surface? And it's, when you think about it, the math is actually quite complicated, and you can actually see it in. Let me see if I can click on here. And I put a lot of comments in my code, but the math is actually quite complicated to determine the level. I mean, there's a lot of things to take into account. So I came up with this thing, and let's see, there you go. And then the result is rather surprising. The result is that it's actually not uniform at all. So the difference between the difference in terms of intensity between the brightest and the dimmest point is actually 81.5%, according to my simulator. And I actually built a prototype version of that, and I was able to confirm, not the exact number, but I was able to confirm that it's actually not uniform at all. So at that point, I started doing some research. Okay, so how do you make a perfectly uniform panel? And this is a problem that has been solved a million times already, because LED TVs use LEDs that are usually located along the bottom and the top rail of the TV screen. And there is what's called a light guiding plate, okay? And the idea behind the light guiding plate is that the light that comes from those LED strips reflect against tiny cavities that are inside that plastic sheet. And then the plastic sheet kind of glows uniformly, okay? So that's kind of the idea. There's many ways it can be done. I don't actually know how TV manufacturers do it. I happen to work for Samsung, but I've never dared to ask. But like, I know some companies, they create acrylic sheets that contain tiny particles. So that's one way to do it. There's another way to do it is to use a laser, and that you focus inside that acrylic sheet and to create tiny cavities. So anyway, there's many ways of doing it. I don't know what people use, but a light getting plate is kind of the secret sauce. So let me show you what I did. Here on the left side, you can see the LED strip, all right? And this thing here is actually the light getting plate. Underneath, of course, there's a white sheet of paper, basically. So where did I get the light getting plate? Well, I went to my local store and I bought a ceiling light, okay, a 12-inch ceiling light, which I think I purchased for like $18, and took it apart. And inside of it, there were quite a few things that I could scavenge. There was an LED strip. There was the background, it was actually a plastic sheet. It was kind of a matte white. And then there was that light guiding plate, which is a piece of plastic that is just maybe like 3 or 4 millimeters thick. And if you light it along the side, along the perimeter, you'll see that it starts glowing uniformly. It's a beautiful thing. So the problem is it was much too big for me. So what I did is I created a template, and then I routed the part. I have a router table so that it would fit exactly my telescope. And so this was the result. And then on top of that, I added an acrylic diffuser. So again, an acrylic sheet that's semi-transparent or semi-opaque. And again, on the router table, I cut it in a circle and just fit it on top. And then there's another 3D printed component that goes on top of it with screws, and it presses everything together. And by the way, there is literally no space between the LED lights and each photosite and the side of the light getting plate. So that was also important. So that's what I did. And then the question was, okay, now it seems to work pretty well. Okay, let me cover the electronics.
On the previous slide, it didn't look that uniform on the left.
Oh, that's big. Yeah, it doesn't look very uniform because it's not pressed together. So there was a little space between the light getting plate and the background sheet. But once you put the acrylic diffuser, there's also like a little spacer. And then when you attach the top and you screw it, it presses everything together and it becomes very uniform. And I'll show you how I measure the uniformity in a minute. For the electronics, it's relatively simple. So there's a little box that's screwed to the top, again, with a USB-C and a 12-volt DC input. I even made a little cover here. Oh, let me try to do this here. Can you guys see me? See my video?
See your video?
Yeah.
You mean your face?
Yeah.
Yeah. Well, on the side of the screen, it's pretty small. It'll be pretty small on the recording.
Oh, I see. Okay. Yeah, I was just going to show you the finished unit. But yeah, you see, it's exactly the size of my telescope. There's a little lip on the inside, so I can just fit it to my dew shield, and so it makes it very easy to take my flats. Okay, let me go back here. So the electronics is relatively simple. In this case, so it involves, again, a microcontroller, which I use the same Arduino SJAA microcontroller. There is a Mini 360 buck converter because the LED strip that I used, technically it's a 12 volt. It's rated for 12 volts, but if you can't power it at 12 volt. If you do, you get a lot of flickering. And when I first saw that, I was like, oh, I must have a bad connection. No, it turns out that I was actually at the limit of what the strip was able to. So I had to lower it to about 9 volts. Also at 12 volt, it was way too bright. So this thing lowers the voltage to 9 volts. There is a power MOSFET, which is used to turn on and off the LED strip. And this is controlled by a PWM signal that comes from one of the pins of the microcontroller. Okay, so here is 3.3 volts, and it controls a system that takes 9 volts and a much higher current. This is 1 amp current to power the LED strip, whereas a pin from the microcontroller can source only about 20 milliamps. So that's why I use a power MOSFET. Okay. So this is what it looks like when it's all soldered, and I used a couple of JST connectors. One for the 12 volt DC input. One is the connection to the LED strip. That's probably one of the trickiest part, is to figure out how you're going to solder and fit everything on a tiny little board. That's probably the trickiest part of the whole project.
Can you control the intensity?
Yes, and the way you control the intensity is by changing the duty cycle of the PWM signal. right? So PWM signal, PWM stands for pulse wave modulation. So you can imagine as it looks like a square wave, okay? And the duty cycle is the ratio between when the signal is high versus the signal is low, okay? So duty cycle of 100%, basically the signal is always high, 0%, the signal is always low, and 50%, it's 50% of the time high, 50% of the time low, right? And the frequency is very high. So if you set it to 50% duty cycle, and if you lower it to 25% duty cycle, you're going to see the brightness go down because you're going to power the LED strip only like half of the time that you powered it up before. By the way, powering an LED strip or a flat panel using a PWM signal can cause some issues. So one of the problems that I have with the very first version of this project is that I was using the default frequency, default PWM frequency of this microcontroller, which I think was 700 Hertz. And so I remember taking my first flat using my luminance filter, and it was a very short exposure, like 0.1 second. And I saw horrible artifacts. And I was like, no, man. So of course, these artifacts would go away with longer exposures. And if I were to dim the panel, but I could only dim the panel so much, first of all. And I was looking for a better solution. So I ended up finding a way to increase the frequency of the PWM signal on that particular microcontroller. That is very microcontroller dependent. And I set it to 20 kilohertz. So now I take flats as short as 0.1 second and they're perfect, no artifacts at all. But that was kind of an interesting discovery that I made when I first tested this project. And by the way, this kind of goes back to one of the core tenets of the maker movement is to tinker and iterate, right? You make a first version, you test it. Most of the times you're going to see some problems. You're going to go back sometimes to the drawing board, or you're going to make some tweaks, experiment some more. So that iterative process, I personally find it very interesting. And that's one of the things that I like about doing this is just it's intellectually challenging. Okay, so I actually evaluated the uniformity of the flat panel. And the way I did that is in the dark in my garage, I put the flat panel and I put my a DSLR camera, and I took a photo of the panel, and I made sure that this was like about 30% ADU. And then I looked at the result in PixInsight, and you can see that it's just like the spread of the histogram is extremely low, extremely small. So, it's actually very, very uniform, which was a really good news. Okay, so any question on the flat panel before I move on to the next project?
I'll ask you one more.
Mm-hmm.
You never see these things for reflectors, with center obstructions. You always see them for refractors. Is there any reason why not, or could you just do that?
What do you mean? I don't understand.
I mean, is there any reason one couldn't make such a thing, a cap and flat panel for a reflector?
Yeah, why couldn't you? Of course.
I don't know. I'm just saying these projects are always shown, with 4 or 5 inch.
I used the tracing panel thing that was mentioned earlier with my RC.
Yeah, I used my tracing panel too on top of my RC. I'm just talking about an automated, closing flat source.
If you guys have an observatory in a large telescope, I would say the best option is probably, it's something I've seen on cloudy nights, where people put their flat panel vertically along the side of their observatory, and when their telescope is in the 0 position, it just points straight towards the flat panel, and then you just turn it on and you can take your flat. So I would actually go this way if I had a bigger telescope and something in an observatory, but I wanted something small because my equipment is something that I want to be able to take to a dark site. So I wanted something small and effective. So yeah, just to go back to your question, the software can actually dim the panel automatically. And it's a really powerful thing because you can have very short exposures for all of your filters, right? I mean, before with my LED tracing panel, even on the highest brightness on narrowband filters, the exposure tended to be a little long, and then I had to manually pause between filters. It was kind of a pain. Now it's completely automated. The software does everything on its own. It changes the brightness of the panel between filters. It does everything. I just press a button and I get all my flats within a minute or two. I don't even have to think about it anymore. It's amazing. All right. Let's talk about the OAG focuser that I built recently. So this is probably the project that I'm the most proud of. And the reason is because I think I came up with something that is unique, that nobody's come up with before. So let me explain what this is about. So I made a little video that shows the problem. So let me explain. On my telescope, I used to use a guide scope. Okay, and I had differential flexure, which caused all of the stars in my exposures to be elongated. I'm sure you guys are familiar with differential exposures, differential flexure. So instead of like spending hours trying to diagnose what the problem was, I switched to an off-axis guider, and immediately it solved the problem. Like, I remember seeing the very first exposure come out of my camera while I was guiding with an off-axis guider, and all the stars were perfectly nice and round. So I was really excited. But then I realized another problem, which is that when I switch filters, and my system switches filters on its own in the middle of the night when I'm sleeping, the focus of the guide camera changes. And sometimes it changes to an extent that PHD2 actually cannot find a guide star as a result, and it starts complaining, I can't find a guide star. So let me show you.
Just to put your OAG, in front of your filter wheel?
The OAG is always in front of the filter wheel.
So then why switching filters matter?
So I'm going to cover that.
Because you're moving your focuser with your
It's because of filter offsets. I'll cover the details, but let me show you what I first saw, and it'll be very clear. So here I'm using Inina on the left, on the right is PHD2. You'll see that, pause here. So I have I'm connected to, so I have the luminance filter selected, and you see that all of the stars look nice and sharp in the guide camera. And I'm going to change to the red filter. And then you'll see what happens to the guide camera. There you go. So you get these little donuts, or they're not donuts because it's not, it doesn't have a separate obstruction, but they're like really bad stars. And at that point, PHD2 will actually complain. Say, hey, sorry, I can't find a good guide star. So that was the problem that I was faced with. And so for the longest time, it was not a huge issue because I was using a color camera. So I only really had two filters, luminance and then a dual narrowband filter. So I would basically image with only one filter throughout the night, right? And then, in the evening, before I go to bed, I would focus the guide camera, and then I would let the telescope do its thing. But since I switched to a monochrome camera, now I have 7 filters, and so this is no longer an option. So the problem really is, let's see. All right, so the problem is caused by filter offsets, right? So because of filter offsets, we have to change the focus of the main imaging camera when we switch filters. And the problem is that your off-axis guider is located before the filter wheel, right? So, so the focus of the guide camera will change. So the solution really is to respond to filter changes. And the idea is to change the focus of the guide camera when you change the filter. But the question is by how much? I mean, you basically have to counteract how much you've moved the main imaging camera, if hopefully that makes sense. So the question is how many steps, right? So we know the offset for each filter because that is something that you have to measure independently. We can know the ratio between a step of the main focuser, the one that controls the entire imaging train, and the little OAG focuser. That's part of the calibration process. And so basically, it's theoretically possible to compute the right amount that you have to move the focus of your guide camera to compensate for that filter offset. Okay. And so the way I implemented it is that that was actually an idea that someone gave me on the Nina Discord server to create a virtual filter wheel ASCOM driver. Okay, so when I connect, in Nina, what I do is I actually connect to a virtual filter wheel ASCOM driver. And within that ASCOM driver, it will actually connect to a real one, to my ZW filter wheel, but it will be able to intercept requests to change the filters. And when I intercept that request, I'm able to also change the focus of the guide camera. So let me talk about some of the mechanical parts because this is a lot of fun. So at first, I experimented with a belt system. So here, by the way, you recognize maybe the ZW helical focuser, okay, because that's the one that comes with their off-axis guider. So at first, I experimented with a belt system. And here is a stepper motor. And it kind of worked, but it would occasionally slip. So I didn't really like this solution too much. So by the way, this thing is just press fitted onto the helical focuser. There's no glue or anything. It's printed with such accuracy that it's exactly the right size, and you press fit it onto the outer perimeter of the focuser. So anyway, so this didn't work too well, so I gave up on this. Then I saw someone on YouTube do 3D printed gears. And so I tried it, and it worked amazingly well. So again, this is press fit onto the helical focuser. This is also press fit onto the axle of the stepper motor. There is no glue involved. And this worked really, really, really well. So here you can see the finished unit. So there's a little guide camera here. This is and here the stepper motor. And the electronics is on the inside that little box here. So the electronics is probably the most interesting part of this project, actually. It's not super complicated, but you have to, I actually did not know how stepper motors worked when I started this project. So I had to do a lot of research, and it's actually not that difficult. And there are a lot of resources on the internet to explain how they work and how to control them. But basically the idea is you send signals that are high or low, and you make sure that they follow a certain sequence on each channel, and that basically makes the stepper motor move. The stepper motor has to, this specific unit is controlled by a 12 volt power supply, and it can take like 0.3, 0.4 amps when it moves. So again, not something that an Arduino can control directly. So there's a ULN 2003 transistor array that allows me to control this. And the LEDs with a resistor, these are just there for debugging. Okay, so this is what it looks like on a breadboard. And I insist, when you do a project that involves electronics, breadboards are amazing. They really allow you to fine-tune your design, test everything before you commit to soldering components onto a PCB. Trust me, that's a really important part. And with this, I was actually you're able to develop the firmware and then test everything properly, and really recommended step. This is the final circuit, so you don't see the LEDs because it's not very useful. The LEDs were there only for debugging. So I used an Arduino Nano clone with a USB-C connector. Again, there's a ULN 2003 Darlington transistor array. This is where the stepper motor connects, and this is the 12-volt DC input. And you can see on the underside all the connections. And then inside the enclosure on the right, that's what it looks like. So what's really unique about this device is actually the software. The software that does that computation to automatically compensate for the filter offset at the level of the guide camera. So when you open the, after connecting to the device, to the virtual filter wheel device, you can open the settings dialog, and this is what you see. So here is the real filter wheel device that it will forward requests to. These are the filter offsets for each filter. And then these are settings like, okay, so this is the focuser that it needs to control, backlash compensation overshoot steps, and then the ratio, what I call the step ratio between the main imaging focuser and the OAG focuser. Again, something that you have to measure once. I even made a small standalone Windows application that allows you to control the focuser to test it. And let me show you the results. So here I connect to, and somebody was asking me earlier, what does it look like when you create your own ASCOM driver? And it actually looks like this. So it's kind of small. I don't know if you can see, but basically it says Dark Sky Geeks filter wheel proxy for OAG focuser. So it just shows up here. But earlier, I think we were talking about the telescope cover, which I implemented as a switch. If you click here, which says switch, you'll see it listed. All right, so here I connect to it. And then you can see the settings dialog, which has all of the important settings. So I connect to it. And so by default, we're on the luminance filter. And so notice that the guide camera is in focus. And whoops, sorry. All right. So what I'm going to do now is change to from the luminance filter to the red filter, which is what I did in the previous video. And then you're going to see what happens. It's going to get blurry. And then immediately after, it's going to correct for it. And there you go. So that was like the haha moment, which is, oh, I can actually deal with the filter changes on my OAG in software, and it actually works really well. So one thing, this is not something that you necessarily, like if you have a mirrored telescope, and or if you have a super high quality refractor, like a Takahashi or Astrophysics, you may not have this problem. The reason I have this problem is because I have a cheap refractor, which is not a really truly apochromatic. And also I use filters from different manufacturers. Okay, so I have filter offsets that are very different. But it's possible that you don't have this problem at all. I would say if you can avoid it, it's better. But if you have this problem, and I know Francesco might have it, this device can be really helpful. Okay. Next project. Any question before I move on? No question. Great. All right, let me talk about SolX and StarX. So let me start by saying that I did not design this product. Somebody else designed it. His name is Christian Buil, French amateur astronomer. And I printed the device myself and I assembled it and tuned it, but I did not design it. So that's really important. So SolX is the Solar Explorer, and StarX is an extension of SolX that allows you to use it for stellar spectroscopy. So SolX is a spectroheliograph. Okay, so it's a high resolution spectrograph, which allows you to take images of the sun in multiple wavelengths. So how does it work? So basically you use a kind of a short focal length refractor and you connect your spectrograph and you make sure that so the spectrograph, by the way, has a slit in the front. So it's going to create a spectrum and of the entire slit. And then you're going to position you're going to move the sun so that it actually there's no light that enters the slit. And then you're going to move your mount so that you scan the entire surface of the sun. And while you do that, you're going to record a movie of basically like a movie of all of the spectra while you scan the surface of the sun, okay? And then you take that movie, you feed it to a software called INTI, and it's able to, and you select a very specific wavelength. So on the left, it's H alpha. On the right, it's calcium, I believe, calcium K or calcium H. And it's able to create or recreate an image of the sun in that wavelength. So from the same movie, it's able to create multiple images of the sun, one for each wavelength that you select. Okay, so you can think of it like the slit would be vertical here, right? And so the spectra will be spread horizontally, okay? And each point of the sun creates a linear spectra, and you're going to move the telescope so that the slit basically moves over the surface of the sun. So you record a movie. So it's kind of a fascinating system, which honestly I had no idea that it even existed until recently. But it's pretty amazing. So full disclosure, I do not do this. I went directly to the StarX module. So I only use mine for stellar spectroscopy. But part of the reason is because I don't have a short focal length refractor. And I'm not super interested in solar imaging, but it's possible to use this project for really high quality solar imaging. Okay. These are some of the first images that I took with my high resolution spectrograph. So this is during the day in my garage without any optics in front of it, just a color camera connected to it. And you move the grading, the diffraction grading, and you can explore different parts of the spectrum. So with the 2400 line per millimeter grading, here you can see about 20 nanometers of the visible spectrum, and the resolution is 0.3 angstrom, no, 0.03 nanometers. Okay, so here's the famous H alpha ray or H alpha line. That's in the red, of course. Calcium H and K, which are in the bluest part of the visible spectrum. Manganese, which is in the green part of the spectrum. So that's actually a triplet. The famous sodium doublet line, which are separated by 6 angstrom. That's in the yellow part of the spectrum. And then if you go towards the infrared, so I think it's like 750 nanometers, something like that, you start seeing what's called telluric lines, I believe. So these are from molecular oxygen from Earth's atmosphere. And you can see these bands, which are actually really beautiful to see. Yeah, those are mostly in the infrared. Okay, so that was kind of my very first experience with this 3D printed spectrograph. So before I go too far, this spectrograph is kind of difficult to print, and I would not recommend it as a, let me go back to, I would not recommend it as a first 3D printing project. It's quite involved, and I had to reprint several parts several times. Like for example, the body here is made of 2 parts, and it's pretty thick. And one thing that happened, I printed this with PETG. One thing that happened is that when the parts cooled, they shrunk ever so slightly. And they were supposed to be 25 millimeters thick, and they turned out to be 24.6 or 24.7. You would think, oh, it's kind of a small difference. The problem is when you put it together, then the hole that these are supposed to go into is no longer the right size. And so it didn't fit. So I had to literally reprint them and print them by scaling the y-axis just a little bit. So there's a lot of tricks like this, which makes this project kind of difficult to print. I know in France, about 200 people built this project, and almost all of them had them printed by a company that actually is run by an amateur astronomer who has a bunch of printers set up in his house, and he's got everything like dialed in perfectly. So that's an option, but I would not have any random company print it for you. It just wouldn't work. So, but it is a fun project. It requires a lot of patience. It's not crazy complicated either, but it does require some experience with 3D printing. By the way, very quickly, how does it work? I should have talked about that. Here, this is the, under here is the diffraction grating. Okay, the camera goes here, the main imaging camera. The light from the telescope comes from here, and there is a slit which is located here. So in my case, it's a 19 micron wide slit. And there is a first lens here called the collimating lens, which basically takes the image of the slit and projects it to like infinitely far. So all of the light rays here are parallel when they hit the diffraction grating. And then it's reflected here. There's another lens, which is called the objective lens, which allows you to form an image of the spectrum onto the sensor. There are a couple of other things here. There's a mirror, which allows you to have the image of the slit reflected towards a guide camera. But basically, that's how it works. And I recommend, if you're interested in this project, I recommend that you check this page here. It's very well explained how the whole thing works. Okay. So the spectrograph by itself is actually not very useful when you want to do spectroscopy. The difficult part is calibration. So calibration basically means, okay, you have a 2D image of a spectrum. The question is, how do you know which pixel corresponds to which wavelength, right? So you would think, oh, you only need one reference. Actually, the problem is you need multiple references because it's not, the dispersion is not going to be linear. So, so it's a little bit more complicated than that. So what you need is some kind of reference that gives you multiple lines, okay? So the way we do this is we use, in my case, I use a neon bulb, a tiny little bulb, which is located in this little device that I made. And you can buy those neon bulbs for Amazon, from Amazon for, I think $9, you get 100. They're a tiny little thing. And they're powered using 110 volt AC. which is why you have this power inverter here. And so they emit light that is monochromatic. There's multiple emission lines from yellow to infrared, and those can be used for calibration, right? So there's software that exists that allows you to get a polynomial dispersion, polynomial rule of dispersion of your spectrograph, and then from there it's able to know exactly which pixel corresponds to which wavelength. You also have to generate flat fields, so to correct for a number of defects, including dust on the sensor is one, but there's also like strange things that happens, and I'll show you an example in just a minute. Okay, so these are some of the things that I made. This is another calibration device which uses fiber optics. There's a little neon bulb inside here. Actually, I show it better here. So there's a little neon bulb. And so this is connected to 110 volts. There's a little resistor here to limit the current. And then you have like little plastic fiber optics, which come out of this device. And then I printed a ring, which I attached at the top of my telescope. And you can see, you see the little orange light that comes out of here? It's lit up by this little tiny bulb, okay? And so what you do is you inject that monochromatic light in the front into your telescope while you're imaging the spectrum of a star, okay? So this is what it looks like. So this is my telescope, my mount. There's this spectrograph, and you can see the calibration system, which injects that neon light at the front, okay? And you inject it while you're capturing the image of a spectrum of a star. So here's what it looks like. This is a 60-second exposure on a famous B star called Chelyabinsk or Beta Lyra. And you can see this is around H alpha, and you can see that the H alpha is in emission, which is typical of B stars. If you stretch this image, this is what you see. So this is the spectrum of that star, right? And you see these lines. These lines actually come from that light, that neon light that we inject at the front of the telescope. And so software is able to know exactly where the spectrum is located. It's able to correct for tilt. It's able to correct for what we call smile, because these lines are not perfectly straight. They're slightly round. It's able to know where the background sky is, so it can subtract the background sky. It's able to find these rays. In some cases, it can identify them automatically, or you can tell them, okay, this number of pixels, this wavelength. And then from there, it's able to calculate the coefficient of that polynomial of the law of dispersion for your spectrograph. And from there, you can generate this, which is a spectral profile. Okay. And by the way, this is really interesting. So with such a high resolution, you can see changes on some targets in a matter of less than an hour. I mean, if you look at a star with a regular telescope and you take a photo, or you look at it with an eyepiece, you're going to see a dot, right? And even with the James Webb Space Telescope, all you can see is the dot. Okay, it's going to have some color, and maybe the brightness can change a little bit, but you're not going to get a lot of details. With a spectrograph, on the other hand, you're going to see a lot of changes. And then nothing stays static. Things can change very, very quickly. Like in some cases, even like half an hour, you can see changes. So this is actually a really interesting case. So the B stars, they have a big accretion disk, which emits in the hydrogen lines and helium in this case. This is helium. And the profile of the H alpha line here, you can actually measure the speed, the rotation speed of the accretion disk. You can see changes in the shape of the accretion disk. There's a lot of really interesting studies that are being done on B stars. So this is kind of a fascinating field. By the way, there is something called stellar tomography, which is kind of an expert topic. I don't know if I'll ever get to do it with my equipment, but some people, definitely professionals, have been able to create maps of stellar spots on stars by looking at their spectra. Basically, what you do is you take many spectra of that star. So it works with stars for which their axis of rotation is more or less vertical compared to like our line of sight, or perpendicular to our line of sight. And the stars have to move relatively quickly, and they have to have large stellar spots. If you have a star that meets those conditions, you will see changes very quickly in say the H-alpha line. And those changes are caused by the Doppler effect. And if you acquire enough data using software that sort of reverses all of that spectral data, professionals have been able to generate maps of stellar spots on other stars. So it's called stellar tomography. And it's kind of fascinating that it's possible to do that with even amateur equipment. Technically, it's possible to do it. Okay, a few other examples, because I think we're running a little long here. Yeah, it's already 9 o'clock. So this is M57. This is kind of an interesting thing. Again, you can see the neon lines here, but this is M57. So again, you have a slit which crosses the nebula. And what you see here is not an image of the nebula. The fact that there's a specific width is representative of the Doppler effect. You can actually measure very, very precisely the rate of expansion of M57, and probably amounts to like 50 kilometers per second or something, I forgot. And you can see, so this is hydrogen. These are nitrogen, quote unquote, forbidden lines. This is helium here. So there's a lot of things we can learn from a spectrum. This is kind of a more exotic object called SS433. Some of you might have heard of it. It's a microquasar located in our galaxy. This is a magnitude 13 object. Doing a magnitude 13 object in high resolution is kind of more than pushing the limits of my equipment, but this shows that it's possible. And you can see again the H-alpha line emission. I'm literally imaging a black hole here. Can you believe it? From my backyard in San Jose. So kind of mind-boggling when you think about it. One thing that I did that was fun, I was able to measure narrowband filters. So I have Ently a 3 nanometer H-alpha filter. So I put it in my filter wheel, attach it to my spectrograph. I put an LED light. And then you take an image with and without the filter, and then using some mathematical operation, you're able to extract this beautiful profile. And this is where H-alpha is. And I was able to confirm that the filter is within specs, which is good. So like I said, I can use the spectrograph in low resolution mode. So in high resolution mode, the resolution is 23,000 in my case. In low resolution mode, it's 900. So this is an image of the solar spectrum. And you can see I also added the neon lines here. And I put some of the main lines. So calcium, H and K, H beta, H alpha here, sodium, magnesium, H gamma is visible. There's some iron lines as well. So this is pretty much the entire visible spectrum. And then I had some fun with discharge lamps. So this is the kind of neon bulbs that I use for calibration. This little bulb here comes from a ballast starter for fluorescent lamps that actually contains a small bulb that itself contains noble gases. And those are fun to analyze using a spectrograph. So like a little mini blue thing gives you this. This is the green version of this little tiny bulb. And then, by the way, there's a little bit of a continuum here, which is caused by phosphorus, which is on the inside of that bulb. And then the ballast starter bulb contains a variety of gases. I was able to identify hydrogen, helium, and argon inside that, that little bulb here. And that can actually be used for calibration. That's one of the reasons why I did the analysis here. By the way, these are 2D spectra, which are generated from calibrated spectral profiles and then colorized in software. And then a few other things. There's an LED panel. You can see here, so first of all, a couple of things that are interesting. An LED, even though the LEDs you see in the street lights, they can look sort of yellow, they still emit a lot of energy in the blue, okay? And this is one of the reasons why I cannot use an LED to create a flat field with my spectrograph, because it's not uniform enough. But you can see that there's some variation here. You see those oscillations? I don't know if you can see very well on Zoom, but that's a pretty common problem, and flat fields are able to correct for this. And this is caused by reflection within the camera sensor, I believe between the camera sensor and the protective window that's in the front. So there's a little bit of interference that happens. This is an incandescent bulb. So that's actually a black body spectrum. And you can see that it emits a lot in the infrared, very little in the blue. So that's to be expected. And this is a CFL bulb, which is what I have in my garage. So I just pointed the spectrograph to the ceiling, and this is what you see. And you can see like lines for mercury, for example, mercury vapor. Okay, one last thing, improvements. So I have a lot of ideas for future projects, and there's one thing I want to improve, and it's my cabling. So you probably noticed that all of my projects use 2 cables, right? One USB cable and one power cable. So let's talk about cabling. This is what I think my telescope cabling looks like. But the reality is, this is what it actually looks like. And I'm sure some of you can relate to this. So it can become quite messy very quickly. So the solution is to actually live in the 21st century. And what I want to do in my future projects is to leverage BLE, which is Bluetooth Low Energy, for communication, right? So to send commands from the computer to the device, you can do it over the air. You don't need a cable for that. In most cases, an onboard battery should be able to power the microcontroller and the components that you're driving. And ideally, you'd be able to recharge the battery in place and maybe provide battery status via an API, so you can control that remotely, and have an on-off switch on the device with an LED indicator. And so I want to test this out soon on a new spectroscopy calibration device that I want to make. That's super amazing. That's going to involve a Arduino Xiao microcontroller with BLE support and lithium battery charging support. It will involve so I need to go from 3.7 volts to 110 AC. So there's going to be a little circuit that does that, which I already tested and it works well. There's going to be a solid state relay to turn on and off the bulb. There's a lot of things involved. It's going to be a lot of fun. And if that works well, I'm actually planning to improve some of the devices that I showed you tonight to basically get rid of the cables. So I think that's where the industry needs to be moving to, is fewer cables, please. I mean, of course, like a camera, probably you'll always need cables. But like just to power the camera, it takes quite a bit of power. So, but in some cases, you don't really need that much power, and you can probably control things over the air. So yeah, I actually received today this little unit and this little battery. So I'm excited to give it a try. Okay, I think we can stop there, and then I can show you that quick tutorial. I prepared a little video if you guys are interested, or we can skip this. Do you have any questions?
There were a couple of
questions, but definitely don't skip.
For the calibration of the spectrum, you used 4 optical fibers on the circular disc, right?
Yes.
Why did you have to use 4? Is that for like rotation, tilt? Why just one is the same as 4, right?
That's
as far as the spectrum goes.
Yeah, that's a great question. So actually, what you saw here, I'm going to stop using. I'm actually going to use only one. There is one small caveat: is the positioning of that light. It has to be. So you still put it in the front of the telescope, right? And the spectrograph sits at the end, but you have to make sure that that bulb is aligned with the slit of the spectrograph, because if you don't, you're going to get a calibration bias. So having 4, basically you can rotate that, and it doesn't matter like how you position it, you'll still get perfect calibration. If you use only one bulb, you have to be very careful about where you position it.
Okay.
Oh, so someone asked about Zigbee. Great question. So I actually have no experience working with Zigbee, but I don't know. That's something that I've heard about. I've never actually done a lot of research, but Bluetooth and Bluetooth Low Energy for low bandwidth communication seems like it's most devices nowadays support that. So it seems like it's not going anywhere. Yeah. Any other question? Didn't this blow your mind that you can do like literally image a black hole from your backyard in San Jose, or see changes in star accretion disks within an hour of time? I mean, to me, this is the real power of spectroscopy. Is you can do like incredible things if you know how to interpret the spectra.
Right, and I think that like on that slide you have, if you go back to that stuff on the right, I think shows you very clearly the rotation of the star.
Correct. So this little thing here is actually the absorption. So there is probably, there may be, so this looks like a P Cygni profile, by the way, and there's probably some absorption, and it's probably not quite centered on the helium line. So there might be like a stellar wind at the same time. So
okay, so you don't think that's just moving away? Oh, I guess that would be, I would be wrong about that, right?
There's multiple.
Not just the left side moving away and the right side moving toward you, or that kind of thing.
It is, but why would it go in absorption here? Like the continuum is here, right? So there's an absorption, there's an emission. Why do you have absorption is because, and if it's if the absorption line is shifted towards the blue, it means that you have a stellar wind. So it's a little complicated to visualize, but it's called P Cygni profile. It's very common, and sometimes there's multiple phenomena that come into the picture. So it can be pretty difficult to interpret spectra, and I'm just at the very beginning of that journey. So don't ask me too many. Go ahead.
Do you calibrate the output? Like you were talking about calibrating the frequency, but do you calibrate the, whatever you want to call that, the magnitude? Or
so it's always relative intensity. I mean, technically yes, you can do it, and actually in this case it is done. You calculate the instrumental response of your equipment by obtaining a spectrum of a known star, a star that is stable and for which we have a known spectrum, right? And then you have to do some mathematical operations between the spectrum that you obtained and of that star, and the reference spectrum, and that gives you the instrumental response. And the instrumental response allows you to get well, the proper profile, first of all, and also, but you know, everything in the y-axis is relative intensity.
All right, well, it's time for let's say one more question, and then I suppose we should let Julien go. Somebody have another question? Okay, well, in that case, there have been plenty of questions, and it's been a great talk, and there's lots of comments like mind equals blown and stuff like that. So thank you very much.
Consider subscribing to my YouTube channel. This is kind of a shameless plug. But basically, I'll be talking about, I really like YouTube as a platform that allows me to share some of the things that I create. And also, of course, GitHub, where you have all of the code and the documentation. But yeah, subscribe to my channel and you'll see that I'll be posting more and more about spectroscopy as I progress along my journey.
All right, so everybody, please unmute and give Julien a round of applause and woohoo and all that stuff. Thank you very much.
Thank you so much.
Thank you very much. Woohoo.
Yeah, it's amazing. Thanks.
Thank you very much, everybody.
Thank you, Julien.
Thanks, everyone. It was great doing this talk, and I'm sure that we'll bump into each other at dark sides or...
Maybe one thing worth mentioning, if you can 3D print masks if you have a Newtonian telescope to remove diffraction spikes, if you are interested.
All right. Well, on that note, thank you very much, everyone. Bye-bye.